Hello everybody, my name is Zainab bin Zaid. I am PhD student in Laboratory Thermal and Applied Thermodynamics, Physics Department, Science and Technique, Faculty of Errachidia, مولاي إسماعيل University مكناس. Allow me to share with you a numerical study of the efficiency of integrating fast change material into a glycerol wall in the Drâa-Tafilalet region. The plan of this presentation is as follows: introduction, problem statement, numerical model, results, and conclusion. Today, improving both energy demand management and supply conditions is a priority that represents a major political challenge for the entire planet. Overall, the building sector accounts for 28% of final energy consumption. It is the second highest energy consumer after transport. In Morocco, this sector represents 25% of total energy consumption, including 7% for tertiary uses and 18% for residential. In the aim of reducing energy consumption relative to building, the integration of fast change materials into the building envelope offers a promising solution. This type of material is capable of absorbing and releasing a large quantity of energy in the form of latent heat. The objective of this new study is to integrate fast change material into a glycerol wall in order to reduce the energy consumption of building in Morocco, especially in the Drâa-Tafilalet region. The underlying notion is to fully utilize the storage capacity in the walls built with client straw. Furthermore, to raise the thermal energy stored in the building envelope, a PCM was integrated into the walls. The geometry of these walls is shown in figure number 1. Four different PCMs are used, which differ mainly in their median melting temperature and composition, as shown in table number 1. The numerical method is based on the finite element method and uses the Galerkin approach to discretize the heat transfer equations in order to evaluate the variations in temperatures and heat flow in glycerol brick. In comparing a PCM, it is necessary to make a number of assumptions. The thermophysical properties of PCM are constant but may be different in the liquid and solid phases: conductivity, specific heat, and the density. The material is shimmed pure, and the change of state takes place at a constant temperature. There is perfect contact between the PCM and the surfaces of the glycerol layer, etc. The external wall surface receives solar radiation, which depends on the orientation south of the wall and time, and exchanges heat by convection with the outside air. A convective boundary condition is applied to the internal surface of the wall under consideration, supposing that the inside temperature is 26 degrees Celsius. The initial temperature of all wall configuration is assumed uniform for all layers. The solar radiation and the outside ambient temperature of Errachidia are shown in figure 5 for days of July from 28 to 31. In this section, the heat fluid density is analyzed to choose the optimal PCM in Errachidia city. 4 PCMs with distinct median melting temperatures are integrated into a clay-straw wall and compared to another without PCM. Figure 5 presents the heat fluid density at the internal surface of walls integrating different thicknesses of PCM's layer. It is clear that PCM 32 has the minimum and the most efficient heat fluid density value compared to other walls and can achieve a maximum difference of 5 watt per meter cube. Finally, in terms of the reduction of heat flow peak, the PCM with a median melting temperature is efficient in the Drâa-Tafilalet region. After we have selected the most appropriate PCM for the Drâa-Tafilalet region, we proceed to the analysis of the optimal thicknesses at the PCM chosen. Figure 6 presents the heat fluid density at the internal surface of walls integrating different thicknesses of the PCM 32 layer. It can be seen that the heat fluid density decreases as the thicknesses of the PCM 32 layer increases. In order to analyze the integration of PCM in traditional clay straw constructions instead of cement constructions, a comparative study is carried out in order to choose the most efficient construction. Figure 7 presents the heat fluid density and the temperature at the internal surface of clay straw walls and cement walls with PCM 32 and without it. The clay straw constructions reduces the heat fluid density and temperature compared to cement constructions by up to 37 watt and 5 degrees Celsius respectively. By integrating PCM 32 in the cement wall, the heat fluid density is reduced with a value up to 28 watt per meter cube. But it is still higher than the one generated by the clay straw wall without PCM. For this reason, the ancient clay straw constructions in the Drâa-Tafilalet region are important. By comparing the behavior of the cement wall and that of clay straw in comparing PCM, it can be seen that the behavior of the cement wall follows the variation of the external conditions as opposite to the clay straw wall. For the last one, when the heat fluid density increases outside, it decreases inside, which keeps the heat fluid density at temperature and the temperature more or less constant because the PCM was partially liquid or partially solid. The fast change is performed. The temperature diffusion, the temperature diffusion is more rapid in cement walls, figure 8a. It decreases by integrating the PCM32, which stores a large heat quantity inside. In the opposite situation, the diffusion of temperature is reduced in clyster walls, and it is again reduced by integrating the PCM32, which stores a large quantity of heat inside. The reduction in fluid density and heat fluid density is estimated in percent. Figure 9 shows that the heat fluid density on the inside and the outside of the walls exposed to the weather conditions of the Drâa-Tafilalet region. The difference between the outside heat fluid density is higher. For the cement wall, it is twice as high as that of clyster wall and depend on the properties of the materials. The integration of PCM32 in clyster wall reduces heat fluid density by 44% and by 40 in the cement wall. By using the clyster construction integrating PCM32 instead of cement product construction, the heat fluid density is reduced by 80%. As a conclusion, in terms of the reduction of heat fluid peak, the PCM with a median melting temperature is efficient in the Drâa-Tafilalet region. For all wall configurations, the heat flow at the inside surface of the wall for the 4 days of July was constant when the PCM was partially liquid, partially solid, and followed the outside conditions when the PCM was completely solid or liquid. By using the clyster construction, integrating PCM32 instead of the cement product constructions, the heat fluid density is reduced by 80%. Thank you.